Hello everyone, sorry for the disruptions because of the internet line, right? So today we will go to the last lecture for this course, right? We will talk about the fluids related applications. Okay, so we will discuss similar to the previous heat transfer applications. Okay, we will spend more time discussing type of applications that you can do, okay, related to the fluids, right? And then at the end we will discuss about the tests. All right, so before we continue, okay, just a reminder, okay, there is an update in the smart hardware. Okay, so whenever you click the attendance link later on, all right, so make sure before you click, turn on the GPS locations if you are using the phone, all right, before you click the link, all right, then allows location in your browser so that we will get your GPS locations. Okay, and after that click check in, right? So all the links for all the classes, okay, will expire on 24th July. Okay, so make sure you go through all the lectures and then take the attendance before that, and we will have tests, 3 tests, okay, to complete this course, right? So we will start with the basic derivations. Okay, we will start with one-dimensional steady state fluid flow. Okay, so here we will talk about a fluid flow going through a porous material. Okay, so we can see pictures there. Okay, a porous materials can be like something that you use to scrap your feet and so on. Okay, so where it allows water to go through. Okay, it can be like a sponge as well. Okay, so water can go through the medium. Okay, and after some time it will become a steady state, so we call a steady state fluid flow. Here when we derive, we consider a one-dimensional steady state, right, which involve only one directions of movement, okay, of the flow. Okay, so we have the Vx, okay, the velocity going into this surface, and Vx plus dx, the velocity going out of this surface. Okay, this surface area we have an area of A. Okay, and the distance of this cube will be the dx. Okay, so this cube we can say as an element itself. Okay, so the length of the elements. Okay, so this is, whereas on the 4 other surface, okay, we will have the impermissible boundary. Okay, so the impermissible boundary means we do not allow any fluid, okay, to go in or go out from that boundary, right? So this is the boundary condition that we set when we derive this steady state fluid flow, right? So generally we will use the conservations of mass. Okay, so the basic equations remain the same, okay, from what you have learned in the fluid dynamics, okay, as well as previous one, the heat transfer. All right, so the conservations of mass, we will say that the mass in to a control volume, okay, in this case is a cube, okay, plus whatever mass generated inside this volume, if there is any, okay, which should be equals to what are the mass going out of that control volume. Okay, so by mass itself, we can always get the mass by writing the density multiplied by the volume, okay, so this is the volume, the rate of the volume itself, okay. So the V is the velocity multiplied by the area multiplied by the time itself, okay. So we get a volume of fluid going in, okay, plus whatever generated, okay. So this Q is the generated one, okay. So again, in this equation, similar to the previous heat transfer equations, the Fourier equations itself, this generated term itself can be positive or negative, okay. So when it is a positive, meaning to say the mass is increasing, whereas when it is a negative one, it become a sink, okay. Previously is a source and sink. Similar to this case, is the source or a sink, okay. If it is a positive one, means the mass increase internally in the volume, okay. So you may have something adding up in that particular control volume, okay. Whereas if there is a leakage, there is something that cause the mass to decrease, then that will be a sink, okay. So we will get a negative sign, okay, in this particular M generated, okay. So the derivations should be similar to previous one, okay. Only the relationship that we use are different. So now we will use mainly based on the fluid theory, all right. So when we relate the velocity of the fluid flow to the hydraulic gradient, we can use the Daisy law, all right. So as given as such, okay. So with the Vx, the velocity going into the inlet surface, okay, is given by these terms, okay. So this term, as you can see, is very similar to the heat transfer term, okay, that we derived previously, okay. The only difference is that this kxx, when we talk about a fluid, okay, going through a porous materials, this kxx is the permissible coefficients of the porous material itself, okay. So when you try to simulate, okay, you can always try to use those established permissible property, okay. In the textbook is given for different materials, okay. The K itself, okay, I think this is missing multiply, okay, right. So now the formulations is very similar. What we do is that when we try to obtain the velocity at the outlet surface, okay, what we have to do is just to use the Taylor expansions, okay, and we take only the first two terms, all right, as previous, okay, or up to your positions that you want, okay. So from there we just put into our equations, okay, the previous equations, and we can derive accordingly, right. So the derivations is similar, only now instead of temperature, this become the stream functions, okay. It can be a potential function as well, right. So it depends on which parameters you intend to use, okay, in this fluid applications, right. Whereas in this Q bar itself is related to the volume flow rate per unit volume itself, okay. So you have the Q divided by the A dx, right. Okay, so now if we extend this one-dimensional equations, okay, into two-dimensional equations, we just have to add the dx and dy. It become partial derivations, okay. So previously this is a differential equations, but most of our application is in three-dimensional, okay. Or if we can simplify, it still become a two-dimensional cases, okay. So it will be useful when we use two-dimensional cases, okay. When we derive it, it become a partial differential equations problem, okay. So we have the these equations given by equations 14.1.10, okay. So again, we can have three type of boundary conditions. The obvious one is if we apply a non-fluid head at the surface, okay, we just apply a non-fluid head, okay, means this psi symbol is the fluid head itself, okay, or the potential itself, okay. Whereas if you don't, if you know the velocity or the gradient, then you can apply the velocity or a gradient value on a certain surface, okay, such as the inlet velocity and so on. Okay, so either you specify the pressure, the fluid head itself on the surface, or the velocity going into a surface or out of a surface, or a combination of them. And also for a surface where there is no movement of fluid, okay, so we can define that as an impermissible boundary, okay, where the velocity going in and out should be equals to 0, okay. So in that case, in the FEA software itself, whenever you don't define any boundary condition, most of the time they will assume that boundary becomes 0, because whenever you don't assign a boundary to any surface, if you automatically do not assign any equations to take away the flow or put in a new flow in the systems. Therefore, if you don't do anything, meaning to say indirectly you are assuming impermissible boundary at that particular system. We can also derive the fluid flow for pipes and also around a solid body, okay. So it is very common to derive for pipes, okay. We can have the pipe networks, okay. Also, when we do a research or when we try to develop a product, okay, we will want to see the performance of that so-called solid body. So this solid body will be subjected to a flow, all right. So instead of the fluid going through a permissible material, okay, so now it can be interactions between this solid body and the fluid itself, okay. So consider a steady state irrotational flow, okay, of an incompressible and inviscid fluid itself, okay. So we will derive accordingly for these applications, all right. So remember, it's a steady state. So previous example derivation, so we talk about steady state, okay. Then the flow itself, we assume do not rotate. So any particles of fluids going into the system will just translate, they do not rotate, all right. And we assume also it is incompressible for these derivations, and the viscosity is very low, okay, in viscid fluids. So this is true for an ideal fluids, okay, ideal fluids where they do not translate, okay. Friction between the fluids and the surface can be ignored, right, and they do not penetrate through the surface. So assuming if you have a wall here, right, a pipe wall, so if you have a fluid going through, so the fluid will just go straight, okay, and this surface will always in contact with the fluid. They will not just go out and create a void, okay. So there is no void, or the fluid will not penetrate the solid, right. So this is what it means by the ideal fluid, right. Say they don't penetrate, they do not stick on the wall itself, okay. So this is the assumptions, okay, when we try to derive for this, okay, which is quite true in most of the case, unless you are dealing with a very specific applications where all these frictions on the surface are become important, okay. If you are studying the surface, the quality of the surface, how the fluids interact with the surface, then this may not be useful for you. Then you have to derive or take into account of other useful equations for you, okay. So for basic applications, for general applications, this is good enough, right. So the velocity of the fluid is related to the velocity potential functions, okay. So here we just assume a potential functions, okay, given by such, okay, in x and y directions, okay. So if we do not consider any heat source, the fluid, the mass source, okay, increase of mass in the fluid or the loss of mass in the fluid itself, okay, then the mass term generated becomes 0. So indirectly the equations now it becomes simpler, right, as such, okay. So if we compare to the previous derived equations for the fluid flow in a permissible material itself, in these equations we can see that these terms basically become 0, okay, and this k term is just equals to 1, right? So now it becomes same, right? So this is a special case, meaning to say previous equations is a general equations that it can apply for other applications, okay. So when we set it correctly, the parameters, then it reflect for the fluid flow inside a pipe as well, okay, assuming the fluid is freely permissible throughout the other fluids, okay. So it's going through the whole volume itself, okay. The basic what we can do now is we apply it for the finite element formulations, okay. The idea is very similar, okay. So we will just go through quickly on this, okay. Once we have the formulations, okay, the idea of how we going to apply that define our functions, okay. So remember, when we derive for the finite elements, okay, we always select the type of elements first, okay, and then we slowly select the functions, okay. So for the fluid we will select the potential functions, and these potential functions, as we can see, since we are using a two-node elements, so we can just apply the same shape functions, okay. The equations will be exactly the same when you derive it, okay, same with the previous ones. That's why the shape function is very important. It represents the functions of this particular shape of this element, right? So different elements, they have their different shape function, but when we apply it for different applications itself, we just use the shape functions, okay. That is why the shape function is very important in finite elements, and they just multiply it according to different functions that they need, okay, in different applications, right? So in this case, it is about the fluid, so we will talk about the hydraulic gradient and the potential relationship, okay, which is given as such, alright. So this is the relationship, and we can combine or break this into two different metrics, okay, and so on, right? So similarly, we have this relationship, okay, just like in the structural side, we derive the stress, the displacement, and the strain relationship, and then we define the strain and the stress relationship, right? So similarly, now once we get this G, okay, the hydraulic gradient, then we will use this hydraulic gradient into our Day's law, right, to obtain the so-called the velocity itself, right? So accordingly, we will have the apply it, okay, into our assembly matrix, okay. What we do is we just combine it according to the nodes, the arrangement of your nodes or the mesh itself, okay. So we can form this relationship F equals to KP, right, very similar to the structural or whatever FEM derivation itself, okay. So we will not go through in detail. So we can only see that it's very similar, right? So we can have this stiffness matrix, okay, as given as such for the fluid applications. So now we will go through into the application, how we going to, what are the considerations and other things that we need to take into account when we do our simulations. Okay, so the first thing is we have to set up our model, okay, our finite element model, FE model. So the problem is when we start a FE model, okay, we cannot we have to put in our values. Okay, so what we do is most of the time we will have to estimate the conditions. Okay, so let's say now we are trying to simulate the fluid flow inside a pipe used for, let's say, maybe deep drilling, okay, for oil and gas or whatever. Okay, so there is a pipe, okay, going through deep sea. Okay, so in this case we will always know that if we drill the oil, okay, we can get the oil property, okay, the viscosity of the oil. Okay, we can do it in the lab. Okay, but then how are we going to measure the temperature of the water in the deep sea? Can we estimate that? Any idea of how to estimate the temperature of water in deep sea? Okay, you can always Google, right? If you know the answer for the temperature of water, you can put in the chat box. All right, then also we may come to another questions like, what if the temperature at this end, okay, so one end of the pipe, okay, is different than the other pipes? Do we have to consider different temperature or the temperature dependence, viscosity or whatever it is for the fluid itself? Okay, when do we need to do all these things? Okay, so also how if we want to simulate a aeroplane, aerofoil, okay, which is moving in the air. Okay, this is a moving object. How are we going to actually model them in the finite model, which in our computer the whole thing doesn't move? Okay, so the only movement that exists in the simulations is the condition that you apply to your finite element model, right? So I will just highlight the temperature of the water in deep sea. Okay, so generally for deep sea we will estimate it as 4 degrees Celsius. Okay, so this is based on the chemistry or the property of the water itself. Okay, where the highest density of water is at 4 degrees Celsius, which means the most heaviest, okay, the most dense water will sink. Okay, that's why in the deep sea we will estimate that as 4 degrees Celsius, right? So this is the idea of how we can estimate the temperature of water based on our knowledge, right? Then also what if the temperature is different, when we should consider, let's say, a temperature dependent viscosity, similar to the previous questions in the previous lecture. Okay, we talked about the temperature dependent material property, okay, the conductivity itself. Okay, so previously we talked about when the temperature difference are very high, when the temperatures go up to maybe melting point, okay, from a room temperature, then in between there is a phase change and other things. Therefore, in that case we would want to use the temperature dependent material property. Similar for the fluid itself. Okay, so if the temperature difference is very high and we intend to investigate, okay, how the fluid flow will increase, okay, or decrease throughout the pumping of this whole length of pipe itself, then we should consider that. Okay, or else we just use an average temperature between the both end. Okay, if the difference is not too high. Okay, so once we get our result, as we know, all this final element result is just an estimate. Okay, so whatever result we get, we still have to validate at the end. Okay, so whatever temperature you use is fine. Okay, but then we have to justify accordingly, right? Then also how to model a moving object. Okay, so as I mentioned, the object is static. Okay, let's say an aerofoil, right? So this object is static, and we define our boundary conditions, all right? And let's say now we want to do a simple two-dimensional analysis, okay? So when we apply a two-dimensional analysis, meaning to say we assume this aerofoil is long enough, okay, to be two-dimensional, okay, or else it will become a three-dimensional cases where the fluid will interact at the tip or the end of the aerofoil itself, okay? So now how we going to model this wing, okay, of an aeroplane, let's say, okay? So what we do is we have to use our basic theoretical model, okay? When an aeroplane is moving, okay, at a certain speed, meaning to say the air itself is not moving, okay, assuming it's not moving, right? Therefore, when the aerofoil is moving at certain speed, let's say velocity of aerofoil, okay, meaning to say it is being hit or hitting the air at the same velocity, right? Okay, so therefore in this case when we model it, nothing is moving, only our definitions of velocity of the flow is changing, okay? So it have to be defined by our theoretical equations, okay? So similar to these examples, we can go through this link itself, okay? This very helpful, okay, where he is trying to describe how to model a flow field in a steel tank, all right? So in his work itself, the propeller is moving, okay? If your computational or your computer is high enough, your software can support a moving solid, okay, while it's doing the simulation of the flow, then okay, it's fine, you can do that, okay? Otherwise, you can do in a way that you draw your propeller, all right? And what he did is he measured the liquid velocity, okay? Just do one measurements, all right, at the end of this tip velocity, okay? So once he get this experimentally, okay, so this become his basis, okay, to run the simulations, okay? That's why simulations, when it start, all these boundary conditions must be as true as possible, okay? If possible, then you can run an experiment to start with it, okay? So what he did, he ran experiment to measure the velocity, okay, profile throughout the tip of it, okay? So once he get it, then it become easy for him to simulate, okay? So he just have to add in the profile, okay, the velocity starting velocity profile, then he can simulate itself, okay, the flow inside the tank itself, okay, while it's steering, right? The LISA FEA software allows you to do the flow analysis as well, okay? It is again based on the FEM technique that we have gone through just now, right? So the only question is now, when we select the type of analysis that you want to run, okay, first of all, when to run a two-dimensional analysis, why not three-dimensional analysis, right? So this is where you have to come into your judgment, okay, your experience, your knowledge, okay, on when to consider a two-dimensional analysis, all right? If the fluid is flowing through a long length itself, okay, so you can easily just use a two-dimensional analysis, okay? But then if it is involving erratic movement, okay, then you have no choice, okay, to consider a three-dimensional analysis, right? For example, if you are considering an analysis of a car, all right, which have a different cross-sectional area, then you may want to do that, all right? But this two-dimensional analysis still provide a good starting, okay, a preliminary ideas, okay? So most of the time, before they do a design, okay, most of them the designer will use this kind of software to simulate. Okay, these simulations provide them an idea. Okay, they don't have to get the exact one. Okay, but then they give you it gives them a general idea of what kind of velocity or drag or whatever that happens. Okay, to give them an idea to select and improve. Okay, before they come to the real or the final dimensions or shape of the product itself. Okay, then also in the flow analysis, we may have a steady state or a transient analysis. Okay, so it's very important to identify when to use steady state, when to use transient. Okay, transient involve changes in maybe the heat sink, the sink or the source itself. Okay, during the flow itself. Okay, so throughout the durations there is something changing. All right, so it can be changes in terms of the velocity input as well. Okay, just like suddenly you want to investigate, suddenly you open a valve. Okay, how the fluids actually move. Okay, then you want to know the transient. Okay, but then if you after a long time, okay, you want to see during the whole operation itself, okay, what is the conditions, then in that case it is advisable to use the steady state. Right, so general case, we just want to know during operation what is the conditions. That's why most of the analysis will be in a steady state. Okay, also steady state is much less computational intense as compared to the transient, right, because of the changing parameters throughout the calculation. So the software have to recalculate and re-enter all these values, right, during the calculations. Okay, so this is one of the examples in the LISA FEA software. Okay, trying to simulate the fluid flow in the pipe. Okay, so what in the tutorial they just fix the boundary, all right, to be impermissible. Okay, and another shape itself which represent the water or the fluid itself under a certain pressure. Okay, so they assign a pressure, they assign the material. This material, they just include the permissivity of the water, all right, and the density. Okay, when you want to know other parameters. All right, so now this courses is all about the finite element methods, FEM, right? But then in actual, okay, in most of the fluid flow applications, those software actually shift to the finite volume methods. Okay, that's why if you see most of the finite element software, okay, when they do for FEM, like the structural, they include heat transfer and some basic fluid flow analysis. But then when they want to perform something like performing a drag for a car and so on, then those software, they code it differently. Okay, they code it according to another principle. They call it finite volume methods. Okay, which we will not cover. Okay, but we just discuss. All right, so you have to see that there is a slightly different technique in terms of the way they solve the equations. Okay, so in the finite element itself, the element is the ultimate thing that we are trying to solve. Okay, whereas in the FVM methods, okay, they will, when they mesh, okay, meaning to say they are creating a volume, right? So instead of an element with nodes, okay, they create a volume and they solve for the volume itself. Okay, they do integrations and so on to solve for that volume instead of the so-called very rigid elements, right? So this volume, they can become bigger, smaller, and so on. Okay, that is the advantage of them, right? So most of the applications, okay, in the software, they apply we call it CFD software. Okay, computational fluid dynamic software. They apply the finite volume methods, okay, instead, right, not using the finite element methods. Okay, so you can see most of this company, they sell the software in two different forms. Okay, one is CFD code or CFD software. Okay, another one is the general structural that we can use for heat transfer as well, right? So it doesn't mean we cannot use FEM to solve the fluid flow, all right, but there is a limitations, all right. So as we can see, if we use the FEM, it is suitable for large problem. Okay, when we involve high speed flow, turbulent flow, okay, this is very important. Okay, we cannot solve turbulent flow in the FEM, right? Remember the previous derivations, we assume the flow is only translational, not rotational and other things. Okay, so whenever there is a mixing or there is a turbulent flow inside, then they have this problem, right? That would be solvable in FEM but not FEM. Okay, also there is a source term like the combustions, okay, which will detect the flow itself. Okay, so you can read more in this link, right? So this is examples of how the abacus, okay, which apply the FEM methods, okay, to solve for the fluid, right? So as you can see, the software itself require you to model the fluid itself, okay, model the fluid itself, okay, mesh it accordingly and assign the fluid property accordingly. Okay, if it is a water, then you assign the viscosity, right, according to the temperature and so on, and run it according to what you intend to do. Okay, whereas in most of the CFD software, okay, then they will define a boundary conditions, okay, or the volume of the test. Okay, so you have to draw the object, okay, and then the software will start to mesh, okay, the whole volume, okay, how it's actually going through, right? So what you need to do is you define your volume of area that you intend to investigate, all right, and then your object, right? So your car is not moving, but the air is moving, assuming similar to the aerofoil itself. Okay, so you have to input the correct boundary conditions, all right, and it will simulate accordingly, right? So again, we just quickly check the LISA menu, okay, LISA FEA menu. So they can use it for the fluid flow analysis. Okay, they can apply it using the fluid potential flow, okay, which is what you have derived previously. All right, so they say is based on the Laplace equations, okay, where this is the velocity potential, okay, which is our previous file, right? Okay, and what is this? This is just the NAMBLA, okay, the NAMBLA square represent the derivative in x, y, and z directions. Okay, meaning to say this is the same, exactly the same equation that we have derived previously, but then now we are considering a three-dimensional, so that's why we include a NAMBLA, okay, for this. All right, so again, we can see the definitions or the assumption is still the same as theory. Okay, incompressible, irrotational is inviscid, right? Exactly the same, right? Because they are derived from the same basic. Okay, and then three type of boundary conditions, okay, that we have discussed previously. No boundary conditions when we do not specify anything, all right, so which represent the wall, all right. Then there we can have the flow rate and the velocity potential. Okay, so this is a general, but some case you may want to most of the software they still allows or encourage you to define the no boundary conditions or the wall itself, okay, because in that case you can assign to define the frictions, okay, interactions between the fluid and the solid itself, right? Then also the fluid flow and the velocity potential that you can define. Alright, so basically this is what we have derived and used, okay, previously, right? So to obtain the pressure result, okay, you must also include the fluid density in the material property, alright, if you intend to get the pressure, right? If you forget to put in the fluid density, then the software will just take a 1 as the property, okay, and you get strange pressure, right? And then we can also use LISA, okay, and it have another options to basically solve using a Navier-Stokes equations, a very famous general fluid equations, okay, to find the steady state solutions. Alright, so this is the equations for Navier-Stokes equations, okay, and again in the menu itself they say when you use this to solve, then the element itself, okay, now this is how they treat it, okay. For each element they will assume the corner node, right? The corner node itself will have 3 degrees of freedom, okay, which is the velocity in x and y directions plus the static pressure, okay, each of this node, okay. Whereas if for the mid side node, okay, for the mid side node, okay, then the software will assume 2 degrees of freedom, which is only the velocity, alright, not the static pressure, okay. So this velocity will be interpolated using the quadratic functions, shape function itself, okay, similar to the pressure interpolated linearly using the shape functions, okay. This is how they do the calculations, alright. So outside phase with no specific boundary conditions are subjected to 0, right? 0 rate, okay. So the n itself is just the direction. It can be x, y, and z, okay. So now the question is when to stop, okay, meaning to say when the software will stop. It can be either success or fail, right? So the software will eventually stop when it reach certain criteria, right? So one of the criteria is that we define it, the software have finished solving the problem, okay, when the relative changes, okay, assuming this is a steady state problem, okay, the relative changes have been reached, or the steady state have been reached, okay, so that the changes between the node field, okay, between subsequent iterations is now below typically 0.0, and you can still change this value, right, up. So once it reaches this, no more changes, we assume it's already steady state, okay, therefore the solver will stop, okay, assuming that is the steady state solutions. So that's why different computer, different time, same final element model, when you run it, if you look at the back, the decimal at the back, sometimes it is different, okay, even though it's the same model, okay, same time or different time or whatever it is, okay. This is because of this stopping conditions, okay. These stopping conditions, they do iterations, and when it reaches this condition, it just stop, right? Then the solutions of each iterations will be multiplied by, we call it relaxation factors, okay. So these relaxation factors will identify what is the next value to try in your iterations. Just like the numerical methods, okay, you have a x or the gap that you want to increase, okay, when you do your iterations. Okay, this is where when you input this one differently, okay, your result will slightly different when it reaches the steady state. Okay, it doesn't mean it is wrong. All right, it's just the way the software doing the estimations. All right, so if we put a high value of 1, okay, it will usually solve very fast, because from one iterations to the next, okay, they jump very fast. Okay, but then it may cause a problem like oscillations. Okay, when it's solved for let's say x equals to 1, okay, and the next one x equals to 2, okay, when it's solved it come to the 2, but then when it doesn't converge, then you have to jump back and so on. Okay, so there is an oscillations in between then. Right, so it depends on how you run it. That's why preliminary test is very important. Okay, you just run once. Okay, if it doesn't work, okay, you have to tune it right accordingly. Okay, so and this menu is very important. Okay, because all the default value they set it accordingly. Okay, so from the menu itself, you know what factors or what values that you can change to improve your results. Okay, then also in many cases when the solver fail to converge, okay, this can be due to several factors. For example, instability, okay, due to the unsteady flow. Okay, as we mentioned, the FEM is not good in solving turbulent, right? So they will stop in that case, all right, because of this convergent problem. Okay, then also there is a sharp changes in the boundary conditions or the geometry itself, and also the last one is the insufficient constraint. Okay, you don't provide enough parameter for it to actually solve it. All right. Then also when we try to solve for the fluid, okay, we have to know there are different type of fluid, and this fluid are very important, okay, to identify which type of equations or solver we want to use. Okay, so for example, in a CFD software, okay, even in LISA, they allows you to have another options like a non-Newtonian fluid analysis. Okay, meaning to say it cater for this type of fluids. Okay, so dependent on the fluid, not all fluid behave similarly. Okay, so you have Newtonian, okay, pseudo-plastic, and Bingham type. All right, so the idea is that Newtonian, as we can see, the flow is like this. All right, the given by the black one. Okay, but then when we come to the Bingham fluid itself, okay, then the flow itself, you can see at the middle, they don't actually pick. Okay, it's almost a flat. Okay, and this profile can be characterized by these equations. Okay, this profile can be characterized by these equations, where this T naught is given by this. Right, so these figures also come from the LISA FEA, because they want to tells you that they can input this one and this one, and from there they will analyze accordingly. All right, so what is Bingham or pseudo-plastic? Okay, maybe Bingham. Okay, so a quick check itself, you can see that this person, okay, Simpson and Jenner, they do tests, okay, on that. All right, so what is those non-Newtonian fluids? It can be your ketchup, okay, your mayonnaise. All right, which again you can see that the value itself, okay, the n value and the k value, right? This is identified through experiments. Okay, and you can see that the behavior is as what we seen in these characteristics. All right, so the type of fluids will tells you what type of analysis you need to use. Okay, because different analysis will use different theory in their code. Alright, so now if you have any questions, you can put into the chat box, okay, while I'm going through the last part, okay, on the applications. Alright, so this paper is by Dr. Chong, okay, where he tried to pre-select, okay, or do a preliminary study on the marine propeller. Alright, so he did a physical model, they scan it and do the model itself, okay, for different marine propeller. Right, so what they do is now what he do is now he put in the middle, right, and this is, as I say, the volume of control volume, okay, that's where the fluid is actually moving, right, because it's in the inside the sea. Alright, so it should be large enough such that the effect is not being disturbed, okay, by the boundary conditions. Okay, so from that he can see that the torque or the thrust and the efficiency generated by the model D, okay, is much higher than the other. Alright, so this give him a good starting, okay, on what dimensions or mean pitch and whatever it is, okay, to design a marine propeller. Right, so this is one way to use the FEM or CFD for fluid. Okay, then another one is by Dr. Sufyan, right, where he's studying what is the suitable length of needle, okay, to explain, right, why it's actually generate a better one. Okay, so this is a spinneret, okay, with the needle. Okay, so you can see that this is the needle itself, okay, and this length from his simulation is will determine the quality of the hollow fiber membrane. Okay, so what this spinneret do is that they are pumping a kind of a fluid, okay, going through this nozzle, okay, and this is a hollow tube, okay, inside is a hollow. Okay, so when it cuts through, it noticed that the nozzle with a length of 39, the length of 39 mm is better than the others. Okay, this one is 34. You can see the hollow is not uniform, okay, whereas the 39 is quite uniform. Okay, so this is the different length of the needle itself. Okay, so what happened or why this happened is that he tried to simulate, okay, because the flow is going at the side. Okay, that's why the fluid is actually not uniform, okay, until a certain length, okay, of the needle. Okay, so it notice that when the length is 39, okay, long enough, okay, the distributions or the velocity across this this needle, all right, so this nozzle needle itself, okay, this is the fluid flowing out, the velocity is almost similar. Okay, it have a range of 0.001, okay, almost similar. All right, so it become uniform. That's why whatever he generate at this length, the result is much better. Right, then this one is how we can estimate the velocity and pressure drop across a cyclone. Okay, so this is a cyclone test bed, okay, where this cyclone is used to separate dust. Okay, the dust can be any particles in the factories, all right, from the air. Okay, so it has been used widely in factories, okay, like the flour factories and so on, to separate the air from the particles that you intend to, right? So this is just an estimations of the velocity and pressure drop across the cyclone itself. So this cyclone works like you are putting in your particles through the air, okay, so it will go inside, okay, and it will spin, okay, due to the centrifugal force. Okay, so it will start to spin, okay, against the wall, right? But when it comes to the bottom one, then because of this smaller dimensions, and there is a so-called collection part, okay, where there is no should I say changes in velocity, okay. Therefore this flow have to do a reverse rotations going up through this suctions fan, right? So therefore, because of the weight of the particles that you intend to collect, this flow will not able to carry the powder or the particles up now, right? Only very small particles can escape through this. The rest will, due to the mass, they will now being collected at the bottom, right, being separated from the air. Okay, so this is the general idea of the cyclone. Okay, so we have the inlet, okay, velocity, and then we can see that at the bottom here the velocity is 0, and then it coming up again. All right, so you can see that the velocity is high at the side, okay, and then throughout the middle it become slower and slower, right? So this length will also very important, okay, the depth of this, so that to avoid the shortcutting, okay, sometimes the air will just escape in this way, okay. This will affect the efficiency of the collections, right? So this is the velocity profile, and this is the pressure profile, right? How the pressure actually drop, okay, because of the suction fan here, okay. So the pressure is very low here, okay. They intend to move downwards and up, right? So this is the comparison between the simulations and the measured value, okay, which we can see that in these simulations is still not good enough, okay. The inlet and outlet velocity is still quite high, all right, for the outlet velocity and the pressure drop, right? So now when we come to prototype and the model, okay, if this is a large prototype or large object, okay, original object, how can we model it in let's say simulations, okay? Either your computer is very powerful, okay, to handle a very large size, okay, when you draw it in the millimeter or in the respective unit, okay, or you can do a scaling, okay. So this will become handy, okay, when we call it a similitude, okay, to predict the prototype performance using a scale model, okay. So this is a widely used model, okay, when they do a simulation as well as the scale model, okay, scale model prototype, okay, to identify especially for the fluid parameters. All right, so in this similitude theory itself, they use a Buckingham pi theorem, okay, where all these parameters, okay, should be a constant, okay, for your model and your prototype, okay. So if you know the value for your prototype and certain value for your model, then you can predict the others. All right, so this is the idea behind it, okay. So when you put it in your simulation software, okay, for a smaller scale, okay, this must comply, okay, so that you can predict accordingly. All right, otherwise it become meaningless, okay, your results. Okay, so this is the actual cyclone installed in the factory, okay. I think this is 3-story high maybe. All right, so as a tutorial, right, so you can try these questions, okay. If, as you can see in this last 2 chapter, we don't go into the examples like in your book, okay, the calculations part, okay, but we focus more on the how we going to use the software and what kind of preventions we need to take care. All right, so this tutorial will give you some ideas of questions that you may expect in your tests. All right, so this is for fluid. All right, so you can expect something similar for your heat transfer problem as well, right? So you can try that on your own.